Math 2414, review, trig identities, quotient identities and their variations. In the previous video, we reviewed the Pythagorean identities by actually deriving them from the Pythagorean theorem applied to a right triangle whose sides were labeled opposite, adjacent, and hypotenuse, and then dividing that equation by either the square of the adjacent or the square of the opposite or the square of hypotenuse, and winding up with these three Pythagorean identities. In this video, we're going to derive and categorize what are called quotient identities. Quotient identities is just a fancy way of saying fractions, quotient being the answer to a division problem, and a fraction being a standard way of writing a division problem. Quotient identities basically answer the question, what happens if I take some of these trig functions and put them on top of others? Now, there are multiple quotient identities and their variations, but there are two primary ones that people see when they learn trigonometry. The first one is what happens when you take sine of theta over cosine of theta. Now, if you have this memorized, that's great, but if you don't, I'm going to show you how to recover what it equals. The trick to this is to replace each of these trig functions with the ratio that they're equal to in terms of opposite, adjacent, and hypotenuse. For example, sine, by definition, is opposite over hypotenuse. Cosine, by definition, is adjacent over hypotenuse. Again, this is if you're using the right triangle definitions. If you use the circle definitions, the x, y, r definitions. Sine is y over r, cosine is x over r, but it would play out the same way. So now we have a ratio of fractions, which is messy. It can always be cleaned up down to one single fraction using a couple of techniques. One technique is to actually do the division problem, multiply the top times the reciprocal of the bottom. In other words, flip this and multiply. The hypotenuses, hypoteni, would cancel. But I want to show you a more algebraic approach besides just saying I'm dividing by two fractions, because I think this skill is a little bit more useful because there are more situations where it can be applied. Flipping this and multiplying really only works when you have one fraction on top of one fraction. But what you can always do inside of a complex fraction, which is the technical name for a fraction with fractions inside of it, what you can always do in a complex fraction to clean it up is to multiply both sides by the least common denominator of the smaller fractions. In this case, those denominators match, and we get hypotenuse. Well, we multiply both sides by hypotenuse, which allows us to do this. And that leaves opposite over adjacent. But that is the very definition of tangent. And just like that, we have one quotient identity. We'll start listing them over here in our list of identities to know. And when I say identities to know, I mean identities to have memorized, if you don't already. Sine theta over cosine theta is equal to tangent theta. Now, like the Pythagorean identities, this quotient identity has some variations by isolating one of its trig functions. For example, in this identity, tangent is isolated. We can multiply both sides by cosine, and that would make it say sine equals tangent theta cosine theta. That would be a version of that identity. And then after that, we can divide both sides by tangent and make it say sine theta over tangent theta equals cosine theta. That would be a variation of this quotient identity. But I'm just going to list the primary one, sine theta over cosine theta. And that is one of two main quotient identities. The other one is essentially the reciprocal of that. In other words, reciprocating both sides of the fraction, both sides of the equation. The reciprocal of sine over cosine is cosine over sine. And the reciprocal of tangent is cotangent. That's easy to see here. If I reciprocate the definition of tangent, I get the definition of cotangent. And those are the two main quotient identities. So really you only have to know one of them. Sine over cosine equals tangent is the one I recommend, because then you just reciprocate both sides of it to get the other. And just like the first one, this second one does have three variations, which you can create by isolating each trig function. In this variation, cotangent is already isolated. If I multiplied both sides by sine, I would get cosine equals cotangent sine, which is a variation that has cosine isolated. And then if I divided both sides by cotangent after that, I would get cosine over cotangent equals sine. That's a third variation of this quotient identity. But again, I would just know these two, or at the very least this one and its reciprocal version, and you're going to be okay. But those are not the only quotient identities. And I'll admit, the other quotient identities, I don't know off the top of my head, but I know how to create them. The reason those two quotient identities worked is because the definitions of sine and cosine, one side of their fractions matched, and that would be the hypotenuse. The general rule is you can create a quotient identity, and I bet you good money that your pre-cal or trig teacher or whatever didn't tell you this. You can actually create a quotient identity by putting any two trig functions on top of each other, provided in their definitions either the tops match or the bottoms match. For example, look at the definitions of cosecant and secant. They both have hypotenuse on the top. Because one side of their definitions match, those will cancel if I stack those on top of each other. So for example, I could create a trig identity by taking cosecant over secant and then just chasing it down algebraically. Cosecant being hypotenuse over opposite, and secant being hypotenuse over adjacent. Now, this one would be a little bit trickier to clean up like I did before if I chose to multiply both sides by something. Remember, when I stacked these up, I multiplied both sides of the fraction by the common denominator. Actually, let's go with that. There's nothing wrong with that. It is a good algebraic tool to have in your arsenal of algebra. Yeah, we'll go with that. If you ever have a fraction with little fractions in it, you can clean up the little fractions by multiplying both sides by the least common denominator. You can clean up the big fraction by multiplying both sides of the big fraction by the least common denominator of the little fractions. In this case, the little fractions denominators are both opposite and adjacent. So I'm going to multiply both sides of this fraction by opposite times adjacent, so that I can do this. And what does that leave me with? On the top, it leaves me with hypotenuse times adjacent. On the bottom, it leaves me hypotenuse times opposite. But now the hypotenuse cancels on both sides because they match and they're both factors. They're both parts of multiplication problems. That leaves me adjacent over opposite. And what is adjacent over opposite? Cotangent. So if we wanted to, I'm not going to, I could put this in my list of identities. Cosine of theta over secant of theta equals cotangent theta. And the reciprocal version of that, which would be secant over cosecant equals tangent. And there are a variety of others that you can create. I invite you to look for some more, but moving forward, I would know these two. And if you see these, then we'll figure out ways out of them. And you don't even have to use the definitions. You can use the third type of identities, which we're about to see, reciprocal identities.